Hey guys, I'm sorry that I'm late. I was in the office hour. Give me a second and then I'm gonna share my slide with you and then we're gonna start in 2 minutes. All right, time is up, guys. Let's start. Actually, let me turn on chat so that I can track it. Okay, guys, welcome back. So this week, as you know that during our YouTube video, we are talking about fast beans and other beans. And then for fast beans, we've talked about use after for vulnerability in the past time, in the last week, but we didn't talk about actually how to attack that, right? So then this week, we talk about how to attack fast beans. And also, we talk about fast beans, use after free and double free, as well as small techniques such as how to lake libc using other beans such as unsorted beans. So I just want to let you know that because of the short of the time, there's no way for me to really talk about all different kinds of vulnerabilities coming from a heap. Like we haven't explored vulnerabilities from say small beans and large beans, and we just touched a little tiny bit about unsorted bean. So this is definitely not the complete set of heap vulnerabilities. But if you're interested in, I would like to share some very useful materials with it, especially the shellfish is how to heap. Actually, Kyle, our TA, he just updated recently. So you can check the GitHub repository of how to heap, and then learn more knowledge in terms of heap vulnerabilities across different versions of glibc. And also, as you have noticed that actually in our class, we use glibc 2.27. It's actually not the updated one. It's not the cutting edge one, which is 2.31. So I choose to share with you, those knowledge in terms of 2.27 because 2.27 does include some very fundamental vulnerabilities that is easy for you to understand. That is also very fundamental, essential, on heap. Also, 2.27, which is the version coming from Ubuntu 18.04, is still a prevalently used Linux version. So I think that it's definitely reasonable for us to use it as a part of the lecture in our software security class. So that's why I focus on 2.27 and I share a lot of very interesting knowledge with you. in terms of the heat. So I want to announce to you that actually today's course will be the last course taught by me in this semester. In the next week, we are going to have our guest lecture coming from Professor David Bromley, and he's going to talk about automatic binary analysis. And specifically, he will talk about fuzzing. So as you see, we have 2 guest lectures and 1 guest lecture talking about, both of them talking about automatic program analysis, especially binary analysis. One is talking about more like reverse engineering or like data analysis, data flow analysis, part of the data of binary analysis. And our future guest lecture will talk about automatic bug finding, which is fuzzing. So I will ship to you a Docker container from which you will be able to get a fuzzing environment. You can also just use that to interact with a fuzzer called Mayhem. Mayhem is a large system. It contains fuzzer. It also contains other components, but we will be able to get in touch with Mayhem, which is very cool. Mayhem is also the winner of the Cyber Grant Challenge from DARPA in 2017. So I really encourage you to capture this opportunity to interact with a cutting edge actual binary analysis tool, actual bug finding tools that has been run in many modern systems and even like military systems. So just get this chance to touch with that tool. I'm very excited about that. I am also very curious and I want to try that by myself as well. So next lecture, David will give us a very nice introduction about fuzzing. I will also be here listening to his lecture. And besides that, we're going to have our assignment 4. You know that it's already started, and I'm so happy today to see some of you guys already started and ask me questions in terms of this assignment. So make sure that you start early. I'm pretty sure that you have learned this from last assignment, which is assignment 3. So, you want to start as soon as possible so that you can have enough time to finish the assignment. And the deadline is going to be October 25th, which is right before Thanksgiving. I am trying my best to give you a good time during Thanksgiving. And also, in terms of CTF, thanks for correction. Yes, it's November 25th. It's not October 25th. October 25th is already passed. Yeah, so it's actually November. No, you don't miss the deadline. Yeah, so it's November 25th. You still have about 13 or 14 days to go. Please do your best on that. And then for the CTF, I'm right now considering about the CTF to be 5 to 7 days. I am in the dilemma of, or I'm hesitating whether or not I should make this CTF challenges starting during Thanksgiving. So we could do that either from Monday to Friday, or we could do that like extend it from 5 days to 7 days so that you can have longer time to work on the challenges. So I really would like to hear you guys' suggestion. If you have a strong opinion, like maybe you want to do that during Thanksgiving so that you have more time to work on that, or maybe you want to make it still after Thanksgiving, just let me know. Yes, I am thinking about poll actually. Actually, why don't I just do that? I'm going to create a poll and then I'm going to send you to Slack. You can vote just like how you vote the president. You can vote for the start date of CTF. All right. And also, good news is that we are reducing the number of challenges from CTF. And also, I was also under the dilemma because I am deciding how many challenges I want to put for CTF. And then, one option is I have less CTF challenges, but then every challenge is going to be accounted for a greater amount of score. That means that if you can't solve one, you just lose a lot of score. I don't want that happen. But then on the other side, if I make every challenge with less score, then I have to increase the size of challenges. So yeah, I just want to let you know that, guys, I am thinking this very carefully, and then I am really, try to come up with a well balance so that you can spend a decent amount of effort to get a decent amount of score. All right, and let me check our chat. I saw there are some questions over there. So question number 1, will it be the same length if it starts earlier? It's not in the same length, right? So as I said, if we start earlier, that means that it will be overlapped with Thanksgiving. So you're probably going to have 7 days. You can have more days to do the challenge. And also, I'm not going to increase the number of challenges. So that means that you just literally have more days to work on that. And then, will the grace period for assignment for overlap with CTF? I don't quite understand what you mean, but like for grace period, you just have 3 days in total. If you use the grace period, then yes, it will be overlap. It's likely that it will be overlap, depending on when we're gonna start with the CTF. So like right now, October 25th is Wednesday. Sorry, November. Okay, November 25th is Wednesday, right? So after that, you could, if CTF starts, say, on Saturday, then if you are gonna have 2 days for your grace period for the assignment 4, then you're gonna have overlapping. And then our CTF challenges individual or group? It's individual. It's gonna be individual for all CTF challenges, as I mentioned in last week. So make sure that you don't cheat. Make sure that you don't collaborate with other people. All right. So nice that I have cleaned up everything. And then today, actually, we're not gonna have a lab, but I want to walk you through for what we have learned during this entire semester. And I'm hoping that this will help you to review all the content, and it's going to be really also especially help you for your future CTFs. Let me go to that page. Give me a sec. Not this. Let me just keep going. Okay, it's here. And guys, I think also, this is going to be a very good chance for you to ask me questions. Like you can even ask me questions from previous content like stack, command line injection. Just feel free to ask me questions today. I think this is really a good chance for you to catch up if you have anything that you don't quite understand. All right. So let me start. We're gonna have a quick, well, not gonna be quick, but give me a second, give me a second, let me close my door. Cool. Okay, so far in our entire semester, we talk about software security, and we basically talk about 2 big parts. One is reverse engineering and the other is PON. So we have introduced a lot of different kinds of binary analysis tools, techniques, as well as software vulnerabilities. So everything is kind of like based on reverse engineering. That is very true, especially for binary, because when you are given a binary, you don't know what's talking about. It's just like 1 0 1 0. It's a bunch of 1 and 0s, and you need to figure it out the semantics. You need to figure it out what the code is talking about. Is it like a crypto algorithm? Is it a specific like data sharing or interacting algorithm? You need to use reverse engineering knowledge to understand what is going. So that's why I put reverse engineering like on the bottom. It's kind of a basic. It's a basic for understanding the binary behavior and then find the bug, identify the vulnerabilities inside a software. So for reverse engineering, the ultimate goal, as I said, is to understand the semantics of a program. And I think so far, most of the program that we give you has the function's name. So you know the name of the function. Sometimes the function's name is pretty straightforward. It includes semantic meaning by itself. It's like you call it win, right? So that you know that this is a winning function. But for many cases, functions may be stripped. And you can just use the command like Linux command strip to strip a binary. So after you strip the function, you will no longer be able to see the function name. If you cannot see the function name, you have to read the code to understand what it's doing, and then to understand what the function is doing. And there are many ways for us to understand. We have a disassembler that can translate from zeros and ones to assembly instructions. And in our course, we just focus on x86 64. But there's also other disassemblers like ARM, a MIPS disassembler so that you can use. Also, there's decompiler that is even more powerful. It can help you to translate from 0 ones to a more readable source code level presentation. You know that you can use Ghidra to get a very nice and free decompiler. IDA also has decompiler, although it's much more expensive, unfortunately. But yeah, you can use either IDA or Ghidra to decompile your code and then read the code in a higher level so that you can understand what the code is doing. Also, usually you want to interact with the code directly. You can run the code and then type the command, type some user's input and see how the program outputs. And you could also use like GDB to debug the code to see, okay, if you print some string, where's the string coming from? If the program outputs some string. So if you take some string coming from the service, you will know where the string coming from. So that is two different kinds of analysis tools that can help you to understand how a program works. Then if you already have this nice skill to reverse engineering a binary, then the next for you is to identify vulnerabilities inside a program. We talk about many different kinds of vulnerabilities. And right now I'm just like divide them in 3 categories. The first one is miscellaneous. It's actually just some kinds of binary, some kinds of vulnerabilities that are not stack or heap, because like stack and heap, they're more broad, they are more general, there are more different kinds. But then for command line injection and then directory traversal, they're both very powerful. You know that you can use those type of vulnerabilities to like leak a file to get a sensitive information if there's not enough check. You can also to arbitrarily execute the command that you specified. Like when I say you, it means like you as attacker, that an attacker can specify. So those two kinds of vulnerabilities, they can be defended in a way that when you program, when you code it, you want to make sure that the command is nicely checked, or even just like don't use system, because system it's tricky. I know that there are some programs that they use system, but if you're going to use system, if you have to use system, make sure that you check command nice enough so that users cannot provide or cannot directly affect command. And then if I also just like recommend you to use something else instead of use system, you want to use Linux like exec and the exec families functions so that you will not be able to, so that attackers will not be able to control command, and you will have a more secure setup. And then for directory traversal, you want to make sure that users input will not contain something that can go beyond the scope of their permission. So basically here I am showing two vulnerabilities. One is command line, and also I show the code. Basically for command line, you want to pay attention to system. This is the problem. And then for directory traversal, here is the problem. You have user input, but then user input, oh, actually, forget about this. So it should also has one, it should only have 1%. And then user input, it can contain something like a ... or ... right? And then in that way, it just go beyond the directory that you specify. And here user can do is that, although it looks like it's fine, it's like user provide probably a directory. What user can do is user can make this as cd, say dot something, or say just like even dot something, and do a and or like a semicolon, and put their malicious codes such as sudo, right? So in those cases, users, attackers will be able to manipulate the execution of the program. Okay. Next, then after we talk about command line injection and path or directory traversal, we then start our adventure in stack. And also after stack, then we talk about heap. Those vulnerabilities that we talk about in stack and heap, they also are called memory corruption. So the goal for us is to have an arbitrary execution, meaning that we want to let the program to execute some code that we want. And when I say the code that we want, it means that we as attacker, suppose that we're attacker, and then we want to be able to let the vulnerable program to execute malicious code. So basically the high level approach is to find a vulnerability and then take advantage of the vulnerability to overwrite an instruction pointer. So here, when I say instruction pointer, it also includes function pointer. And those instruction pointer will be overwritten, replaced with a malicious code pointer, so that later on, when we call the function again, or when the instruction pointer is used again, it will go to the malicious part of the code. So here, there are three parts: vulnerability, instruction pointer, and malicious code pointer. I'm going to start with the second one first, which is instruction pointer. So instruction pointer, throughout our entire course, we talk about three different types of instruction pointer. The first is the saved return address, and this is on stack. And then the second is a global offset table. This is in the GOT section, which is also the data part of the code. And then the third is the hook functions in glibc. So this coming from glibc library. It comes from the data segment of libc. Okay, now let's continue. Then for malicious code, we need to find a place for us to store the malicious code so that attacker can fulfill their malicious purpose. So one way is to find a function that we can take advantage, right? This is coming from the vulnerable program. And then if vulnerable program doesn't contain a function that we can use directly, then we can create the code by ourselves and then want to store it somewhere. So if we're going to use shell code, then we want to put it in stack. But then the code itself is created by attacker. Okay, and then the third is rob gadget. So the gadget itself is also stored in stack. And here I mean the rob chain. The chain is stored in stack, but the code is actually not coming from attacker. The code is coming from the program itself. It can be coming from the program. It can coming from the dynamic linked library, which is like libc, when the process is running. All right. And now let's continue. Then let's start to talk about vulnerabilities. So for stack vulnerabilities, we talk about Stack Overflow and format string. So for Stack Overflow, the high level idea is that you just want to find a buffer and then you're going to overwrite it all along from the buffer to the saved return address. And then you overwrite the saved return address, make that to point to a malicious instruction. And then going back here, we know that we can use the winning function. We can have it pointed to shellcode or a rob gadget. And then next, we talk about format string vulnerabilities. So for format string vulnerabilities, I am checking the chat and then noticed that some of you are talking about format string, and then maybe you'd like me to walk through format string very quickly. How do you guys think about that? Yes? Okay. Yeah, let me just quickly walk through this. And then I think this page should be well enough for us to explain what's happening on format string. Actually, let me just write one more statement, which is the print statement. So it has printf, and then just do a buff over here. All right. So then for format string, first of all, this is printf, right? And then according to x86-64's calling convention, this is the first argument, right? And then if you still remember, the first argument stored in RDI, register RDI. So the way that it works is that it will first check the address, check the value of RDI for the register. And then this register will store the pointer, the address of the buffer. So RDI will point to the address. And then here it's going to point to this place, right? And then for attacker can change the content over here, like just make it up so that for printf, when it scans this, when it scans the format string, it will start to realize that, okay, there are how many arguments that will be followed by this format string according to the specifiers in the format string. So in this case, we found there is a, first a %x with some more format specification, but here this is one argument, right? Let me just write here, 1, right? And then this is second, 2, 3, 4. Yeah, this is a number 1, 5. And then here is a %n. %n means that is also another one. Actually, this is 6. Give me a second. Let me just erase it. It looks too sketchy. Okay, so this is number 6. And then for the first 5 ones, they're all %x, right? And then it means that it's going to output something. It means that according to the format string, printf knows that it needs to look at 5 or more arguments to print, and then the 6th argument is to store something. Like this is because of the specifier. This is because of n, nature of %n. So it means that it's gonna write something to some place. Okay, then the next is, let's just figure it out what it does for those first 5 print. We know that it's gonna go for 5 arguments, right? So for that 5 argument, what it's going to do is that it needs to find that 5 arguments to output. And then we know that this is already the first argument for printf. So printf then will go to look at the other argument, which is argument RDRSI, right? And then I think it's RDX. I actually forgot some of them. I forgot the exact order of the register, but you know that there is 6 registers that's going to be used to store those arguments according to the x86 64 calling convention, right? So after that 6 registers, then it will start to look at stack. So then in this case, what we want to do is that we want to make sure that after that, we want to let this 6 argument to write to the right location, right? So here, we know that this is the 6th argument and it will start to look at stack. But then where do we need to look at? We know that this is the 6th one, the 6th, why it disappears? Sorry, give me a second. I am really bad at using my iPad, right? So this is the 6th argument, 6 specifiers. And then let's take a look at this. What is that? Is %, let me write here because it's already messed up over there. $n, right? So if you look at the specifier here, you found that this is the numbers. You want to find the 11th argument in the printf function. So this is the 6th specifier, but it has this numbers of argument specification over there. So that means that we want to find the 11th argument. And we know that the first 6 argument, including buff, coming from registers. So, and for this is gonna be the 11th. So that we need to start to look at stack, and we know that where the 11th argument is, right? So looking at the format string, we want to count 11s. we know that there is 5 more over here, right? Because there are 6 registers in total, but then the first register gives to buff. And starting from RSI, there will be 5 more registers for the argument. And after that, right, remember, it's after that, it's going to go look at the heap. Look at the stack. So this is 5, and then this is going to be the 6th one, 7, 8, 9, 10, 11. So here is the place. Here's the start of the 11th argument. And then printf find out, okay, where is this? And then what is this talking about? So in fact, that in the 11th part, it stores 8 bytes. And then that will be considered as a memory address that this %n wants to write to. So this is the way that printf works. I hope that this is clear enough for you to understand how printf works. And then now let's talk about how to utilize this and how to make it as an attack. Okay, so now let me just clear this up, and I'm going to talk about the attacking process. Now we're coming back, right? And then let me write the printf, print buff again. So we want to come up with the buff string by ourselves. And then first of all, you need to make sure that where you want to write and what value that you want to write, okay? And then after that, I usually start with this first, because right now I know that I need to write 1,000 bytes before I specify the address of here, right? So when I start, I will just maybe write %n somewhere. I know that this is the end that I want to be able to get overwrite. And then I want to make sure that before that, my format string will be able to output 1,000 bytes. So how to make it output 1,000 bytes? I mean, one way is just put 1,000 A's, 1,000 whatever, everything. But usually we don't have enough buffer. Our buffer usually is not long enough to put 1,000 bytes over there, right? So that's why we want to take advantage of format specifiers. And this is why I am using a format specifier such like this. So when I do %0 to 100x, it means that I want to output a number in the format of hex. And it doesn't have to be hex. You can make it D. You can make it like whatever base. But then you want to specify this 200, meaning that you want to extend the output of the specific argument to make it as 200 bytes. And the reason why I put the 0 here is just because that if, usually the integer is not it's not long enough to support 200 bytes. So you definitely need some padding. And here I'm specifying the the format of padding. I'm telling it that when it's output and when a padding is necessary, you want to pad it with 0. So that's why I put a 0 over here. So 0 at the beginning, followed by the number of bytes that I want to output, and then the format, like the decimal or hexadecimal, the format of the integer. And then after that, we know that this will help us to output 200 bytes, right? You don't have to make it like 200. You can make it like 500. It's really up to you. Right now I just show a random, like one way that I craft it is to use 200. But then because I'm using 200 right now, I know that I need to have 5 200, right? So that's why I put 1, 2, 3, 4, 5. So after that, I know that at this point, I am able to output 1,000 bytes. And that is the time that I need the format string to output something to store to the address that I want, right? So then next I'm gonna do is I am going to, put this times 5 and then followed by this %n. Let me clear this up. Followed by %n. And then I know that I need to put the address. So I put the address after this. Right now, I just like right after this. I'm just, don't write them all. I just put some address. Okay, I'm just put 5555 for an easy representation. And there's more. Like that is the address. And then I'm start to put it into a stack and see what does it look like, right? So that's why you want to have a stack, and that's why you want to start to write this down. And then every time you want to write it like every row is 8 bytes. That's the way that printf observe arguments. Like for printf, 8 bytes is one argument. So you put them down and then you find that, okay, right now you have 1, 2, 3, 4. You have 4 arguments. There's still not something over here. Like this is kind of a blank right now. You just put into the stack and then that is followed by this address. Okay, now this is not good because first of all, we want to align the address so that this entire address will be taken as a whole as an argument for printf. This is one thing that we need to resolve. I'm going to write it over here, which is alignment. And then it's also not good because of argument. Because once I start to put those format strings over here, from printf's perspective, those is going to be the more argument in printf, in the printf function. As I mentioned, for calling convention, buff will be the first argument, and it's going to be stored in a register, right? It's just going to be RDI. But after that, there is 5 more register. So from printf's perspective, this is going to be the first argument after this 5 more register. So it's going to be from printf, it's going to be the 6th argument. But let's pause here and pay attention. But from the format strings perspective, I'll just write buff. From format strings perspective, this is going to be the 5th argument. Oh, actually, here when I say 6, it means that starting from 0 to 5, that goes to register. And then here for buffer, it's going to be the 5th one, which is also from 0 to 4. But for buffer, when it specifies those arguments, it starts with 1. So here, if you're going to start with 1, then this is going to be the 6th argument if you start with 1. So then that's why here is the 6th argument for buff for the format string. And then this is the 7th. This is the 8th. And then this is the 9th, right? And then this is going to be the 10th. And the next for me is, okay, I know that this address is not aligned. Let me align this first. And then that's why I put this address here in the 11th, because I realized that this is the only location that I can put this address and also have this specifier inside my format string. But then I realized that I probably need something to, pad this up in order to make the address aligned. That's why I put a pad over here, just like something 4 bytes that is good enough for the address starts with something like make the address align with the 8 byte. All right, so that's how you can come up with a format string. So basically some steps. First step, coming up with this part, right? This is the first step. And then step number 2 is to find that given those format string, what is the number of argument that you want to put for your actual address, right? That is the number 2 part. And then you need to start to twist so that this address is aligned with 8 byte, and also you can still have enough space to put the specifier for %n for this specific writing. That's it, 3 steps. All right, now I'm gonna move on. And then next, then we start to talk about heap. We talk about basically two parts. One is Tcache and the other is fastbin. So Tcache has 3 different kinds of vulnerabilities. Although again, this is not complete. Like just in our course, I talk about 3 different kinds of vulnerabilities. One is Tcache used after free. So the high level idea is that once a chunk is free, the chunk goes to Tcache bin. And then we can still add the chunk, although it goes to Tcache bin, we added the chunk so that the chunks part, the part that is supposed to store the forward pointer, is added to point to a victim chunk. And after the victim chunk is pointed, then you can use 2 times of malloc to get the victim chunk, which contains the victim memory, such as GOT table. So then you can then overwrite the instruction pointer, overwrite that with a malicious pointer. And then for double free, it's slightly different, but the high level idea is the same in the sense that you still want to change a forward pointer inside the data chunk, inside the chunk, so that the chunk will link to a victim chunk. But the way that you make it work is that you want to have a same chunk free for twice, so that when this two identical chunk got malloc for one time, then one of the identical chunks will got returned from the malloc, and then user, like this one coming from the malloc, so that user can start to add it. When user added it, free chunk is also gonna be added, because when malloc returns, it's gonna just return the memory. I'm gonna put an arbitrary value over here, such as 5555. And then when this chunk returns, when you look at the Tcache, it's also here is 5555. It's the same. So that's why when you allocate it, here it's also gonna be changed. And then if you look at the Tcache bin, it will look like this chunk linked to another victim chunk. And the third vulnerability for Tcache is Tcache overflow. So for Tcache overflow, the idea, also the high level is the same. You want to add a chunk to let it link to a victim chunk, but the way to edit it is different. The way is that suppose that you have another chunk before the chunk 1. Like in this case, suppose that you have chunk 0 that is before chunk 1. So what you want to do is you want to keep writing chunk 0. It's like stack overflow, but it just like this case is gonna happen on heap. You overflow chunk 0 to let it all keep writing. After chunk 0 is gonna be the metadata part of the chunk 1, and then it's gonna be the forward pointer of chunk 1. Oh, it's actually here. Sorry. So you overwrite this part of the data so that even though chunk 1 is frayed, you still be able to change this to a victim. So you want to point it to a fake chunk. And then in this case, once you malloc twice, and the second time you're gonna get the fake chunk, and then you can overwrite it. All right, and then next is fastbin. In fastbin, we talk about two different kinds of vulnerabilities. One is fastbin use after fray, and the other is fastbin double fray. For fastbin use after fray, the idea is similar to T-cache-bin's use after fray. The only difference is that you want to make sure that the chunk needs to satisfy an additional condition. So you need to make the fake chunk to point to 0, 0, or like just have the 0, 0 here in a forward pointer, such that when T-cache refilling is happening, it's not gonna raise an error. Or you could do is that you have fake chunk, but then those fake chunk is like pointing to other chunks, and then like for many times, but those are all dereferenceable. You want to make sure the forward pointer here is all dereferenceable so that it will not raise any error when T-cache is refilled. And also you want to make sure that like if there is a place that you just cannot do a hold on, sorry, let me draw this more clear. Even though there is a chunk, and draw this a little bit larger so that you can see this clearly. This is the key part. If this chunk is cannot do a forward pointer, but if you just start to count from the second one of the fastbin to this failing chunk, if you have more than 7 chunks, you're still good to go. This is because of T-cache refilling. Like T-cache refilling will only refill 7 chunks in T-cache bin, because T-cache bin will, in maximum have 7 chunks. So that's why if you don't have a very good dereference here, if there is a dereference error for this forward pointer, it's fine as long as there is already 7 chunks over here, so that when the refilling is happening, it will stop before this dereference error. Okay, now let's continue. This is about fastbin. Then for double fray, fastbin double fray vulnerability, this is like I would say it's similar to T-cache bin's double fray, but it's different, and it's more different than the way that than the difference between fastbin and T-cache bin in use after fray. So for fastbin double fray, again, you want to make like same identical chunk in one fastbin. But here, first you want to make sure that when you have 2 identical chunks, they're not pointing to themselves. So you really need to have another chunk in the middle, because if you just link 2 chunks without this, then it will raise an error. So make sure that you do. Oh, sorry. Okay, make sure that you do contain this some chunk in the middle. Okay, and then next, oh, that's it. Okay, let me just say something more about fastbin. And then you want to make sure that you understand the order of the, of the entire process clearly. This is very important, the order. When the fastbin's chunks got refilled into T-cache bin. And if you're not clear about that, please go check the videos that I just posted this week. And that is very, very important, because if you messed up the order, you will not get you will not do malloc later on malloc correctly to get the victim chunk. So make sure that you understand that. Okay, then after that, we talk about all different kinds of a defense. We mentioned them when we start to talk about stacks, the stacks vulnerabilities. we basically talk about 4 different kinds of defense mechanisms: stack canary, NX, like non-executable for data segment, for writable data segment, and then ASLR, and then PI, positional independent code execution. So for this 4 kinds of defense, first is stack canary. Because of a stack canary, you need to make sure that you can bypass this correctly. Basically, stack canary is additional bytes that is stored in stack, so that while you overwrite it, it will be checked, it will be trigger a failure in the end of a function. So you want to make sure that if you overwrite a stack, you either just don't touch stack canary, or you could just overwrite the stack canary with the same value, so that when stack canary check is happening, it will not detect a violation. It will not detect a change of the value for stack canary. And this refers to videos that we have for week 6. So if you don't remember that, feel free to check the video in week 6. And we mentioned 3 ways to mitigate stack canary. One is to leak the value stored in stack canary, so that you can overflow it, or you can overwrite it with the same value. And then the second is to overwrite the predefined canary. So predefined canary is also reside in stack. So if you can have a huge overflow, then you can just like overflow all from the current function stack, all up, go lower address, go actually higher address until you hit the predefined canary. So you can change the value over there, which will also change the value over here in your stack. So you want to change the both places. And as long as you make these 2 places same, you're good. And then the last one is to change the function stack check fail. Stack check fail will be invoked when stack canary fails, like when there is a misalignment with the value put into the current call stack and the predefined canary. So you can also just figure out where stack check fail, where it is, and then change that function pointer to somewhere else. Like you can just make a like a hex 90, which is like no op. Redirect stack check fail to a place that has only no op, and then return, so that even though stack check fail is called, it will not raise an exception. It will just like keep executing. Okay, and then the next is NX, is non-executable stack. So because of that, we will not be able to execute stack anymore. And because of that, if we look at the malicious instructions that we can put, you will realize that we can still use winning function, because winning function is not on stack, but we can no longer use shellcode if you put shellcode on stack. So we cannot do shellcode anymore, but we can do rob gadget, because rob gadget, the code itself, as I mentioned before, the code itself is not on stack. The code itself, the actual instructions are from libc, which is still executable. All right, and then next is PI, positional independent execution. When PI is enabled, all the code, they are position independent. That means that the code will only having in like an offset to the base of it, and then the base is unknown. So you need to be able to get the value of the base address of the code when the code is loaded. So also, because of the nature of global offset table, if you remember like the PLT session in the binary, the way that I find a global offset table is to use the offset of the current RIP, which is the current instruction pointer. So when RIP is got like position independent, That means that RIP will equal to a current base plus the offset. And when you look at the binary itself, you will only be able to get the offset, but you will not be able to get the base. So in that case, you will also not gonna know where the global offset table is. That's why, for global offset table, if you're on a overwrite global offset table, and if you want to identify where the global offset table is, you need to know the base of the current code segment. So therefore, for winning function, if you want to know where the winning function is, you need to require the base of the code segment. And for shellcode, you can still use it because it's on stack. It's not going to be changed. And then for ROP gadget, because ROP gadget, the ROP code is in libc. And then the libc is also going to be dynamically linked. So there's offset only. You also need to know the base of libc. And therefore, for winning function and then for ROP gadget, you need to know where the base of them. However, the nice thing is that for Pi, the base address will not be changed. So if you just run or interact with the malicious service, and then if you just run that in that particular environment, as long as you know where the base of it, you can just keep using the base constantly, since it's not going to be changed because of Pi. Then the next is about ASLR. This is the tough part, because even though Pi is not going to change the base of the address, ASLR will do. In this case, the base of the code, as well as the data, meaning that the base of the stack, the base of the heap, will also be randomized. Then Then for winning function, you need to get the base, and you need to require the base of the code segment every time that you interact with the service, since it's going to keep changing every time you call it. And similarly, for shellcode and ROP gadget, you also need to get the base, and also you need to make sure that you get the base in the same time as you interact with the process. You cannot do something like you run the process for first time, you get a base, and then you run the process for the second time, you restarted it, and you use the base, since the base is going to be changed. All right, and then this is the pawning part of, again, for instruction pointer, you can find this 3 different places that you can overwrite to. And then the last, I think this is going to be very helpful to you. I put all those in a table. Basically, for you, you need to identify where you want to write, which is like victim, function, or instruction pointers, where you want to overwrite. And you want to then figure it out what value that you want to overwrite, right? So you can overwrite the victim place with winning function, or the shellcode, the start of the shellcode, or a ROP gadget, like the chain. Then when NX is enabled, you will not be able to use shellcode anymore. And then when Pi is enabled, you can still use shellcode. You can, overwrite. You can get the same return address in the same place all the time, since it is on stack. However, for everything else, for global offset table on trace, for libc hook functions such as malloc hook, and then for winning function and ROP gadget, they're all going to be offset. So you need to get the base. And the nice thing is that the base is going to be constant. So you can just run the process for first time, get a base, and then repeat it. Run the process for the second time, and then do all those exploits using offset that you get before. And then for ASLR, if ASLR is opened, is enabled, then everything becomes a base. And everything you need to, find from the same process. You need to make sure that you don't break out during the process keep running. And during the entire process, you need to get the base address of maybe the libc, or maybe the program, or maybe the stack, or maybe the heap. And starting from there, you want to add your offset with the base in order to get the actual victim address and then the actual malicious code location. All right. That's pretty much for our entire course, entire semester's content. And I know that for you, this is probably a pretty challenging course. I hope that you do learn a lot from this course. And also, I very appreciate your guys' support, your guys' effort putting into the course, like including the videos, the lectures, the slides, the in-class lab and assignment, and also, the future CTFs. For me, it's really a pleasant um, experience for me to interact, to talk with you, and try to understand, what is good, what is bad in my course, and then also it's good for me to learn how to improve this course in the future. But ultimately, I think for me, it's really, really nice that I know you guys and then meet you online, although we cannot really meet in person. And I really happy to see that we have very active discussion in Slack. And also I want to especially thank those students that helped me answer questions on Slack. I know that some of you got DMs from other students for specific questions. You also just answer questions publicly, which I also very appreciate. Also, my team is looking for potential students who are interested in doing binary analysis research in the future. So if you're interested in, feel free to shoot me an email. We can chat. Also, I'm looking for TAs for next semester. I'm gonna teach a undergrad level computer security. And if you are interested in that position, you can also give me a message, and then we can chat and decide whether or not you fit for that position. Yeah, I think that's pretty much it for the course. Now I am very welcome to any questions that you ask. And also I will stay here for probably like a little bit longer for you in case that you have more logistics issue as well. And in terms of the poll, I will create that by the end of this week. So it's going to be definitely before our CTF so that we can decide when we want to start. Cool. That's pretty much it. Thank you, everyone.
I have a question on I think it was the stack security part when we're talking about overriding stack check fail. Like,
Yes.
how would you do that because stack check fail would be called before overriding the return address. So would you have to like overwrite it like through like a heap exploit, or how would that work?
It doesn't have to be heap, but you're right. You have to overwrite that before this vulnerable function is called, like before you overwrite the stack canary. Basically, you probably want to utilize other vulnerability. You want to make your attack into multiple steps, and in previous step, you overwrite stack check fail.
So what would be an example of that?
I don't have an example right now, but you can just consider that as, for example, a heap that you can change stack check fail. And then using a heap vulnerability, you overwrite that. And maybe there is some reason that just stops you from overwriting malloc. For example, you realize that actually you cannot really overwrite malloc. You have to use a malloc function again in the future. So the heap vulnerability, although you can overwrite something, you cannot overwrite those key functions that you will still need to use in the future. That's why you can consider that to overwrite stack check fail, and then utilize another buffer related vulnerability.
So could you like overwrite stack check fail with like no ops?
Yes, you can do that. Yes.
And I didn't know you can actually like overwrite the canary because whenever I see it on the binary, it exists like really at like a strange location.
Mm-hmm.
So you can actually like with a large buffer overflow, you can actually overwrite it.
Yes, you can do that.
Sorry, when you said that we could overwrite stack check fail to be a bunch of no ops, I think isn't it a function? It's a function that we call, right? So if you overwrote that with no ops, wouldn't you like jump to its position in the table and then just kind of fall off the bottom of that? Maybe I'm not describing that in the best way, but like I feel like if you were to overwrite stack check fail with something that is like equivalent to a no op, you would probably want to make it like a return and not like
Right. Yes. Exactly.
Okay.
Yes. It's not only just no op. Like you want to make sure that they return so that you can come back to the current stack.
Yeah, that was a good catch. So will the CTF have like, is it like a multi exploitation type challenge for each one, or I was just wondering how that would look.
So for CTF, it's we're still coming up with challenges. So I cannot give you a conclusive answer, or very determined as that yes, there will be multiple, there will be a challenge with multiple vulnerabilities, or something like, oh no, there is not, like every challenge is single vulnerability. It's more of like open-ended. You probably want to be prepared for either situation. All right, guys. If you have no more questions, then let me stop recording